Okay, let's set up a couple more examples here. So I'd like to find the line integral of the vector field f arrow of x comma y is equal to angle bracket x cubed y comma 1 plus y squared over the curve C, where the curve here is actually going to be um, the following curve. So it is actually x-axis, y-axis. The curve here is actually given by y equals cosine of x. It's just the standard cosine sine wave traveling that way towards the right. So we are going to need a parameterization, and we're going to need to write that in the form of a vector function, right? So a vector function for describing C is, well, r of t equals, well, how about the x coordinate is just t itself? So x and t play the same role here. And then the y value, well, can just be cosine of t. And we'll just do this t going from 0 to 2 pi, right? Because the x ends at 2 pi here. All right, so then this thingy right there, t, that's x of t in this example. And then cosine of t, that's y of t in this example. Now, we're going to need two things out of this. So one of the things that we're going to need is f of r of t. So we need to compose this with that. Make sure to do this in the right order. In the end, we need something that is only going to mention the variable t. So make sure you're feeding which thing into which, right? So there's two things here, there's two things there, and sometimes people kind of mix up what you need to feed in where, right? So what we'll have here is angle bracket, let's see, x cubed, so t cubed. Y is cosine of t, okay? And then 1 plus y squared, so 1 plus, well, y is cosine of t, so cosine squared of t. Okay, so that's f of r of t. Then we also need r prime of t, so we should just differentiate the vector function that we cooked up here one component at a time, so 1 comma negative sine of t. Now, we just piece everything together. Right? So the integral over the curve C of f arrow dot d r arrow is the integral from 0 to 2 pi, those are our t values, of this thingy dot that thingy. So if we just stare at this vector and just do their dot product, we should have, well, t cubed times cosine of t times a 1. So what, t cubed cosine of t. And then plus we have this thingy times that thingy, right? So let's just be a little lazy about it. How about 1 plus cosine squared t in parentheses times negative sine of t. Okay, technically this should all be in parentheses. I'm not really all too bothered about that. And then dt. Okay, so I'll just say that you can split this up. This at the sum to create two separate integrals. This one over here, if you'd like to do it, isn't so bad. If you just do a substitution of a u is equal to cosine of t would probably do it, right? So we won't, or yeah. So let's not work through all of that here. Over here, the work would be a little more because of the t cubed times cosine of t. It can be done, but this would be multiple times through an integration by parts. Okay, I'm just mentioning that just so that you have a little bit of setup if you want to go for it. So this integral can be computed. It's a little bit of a good reminder and challenge, so you might as well give it a try on your own. But I'd like to instead set up another one, right? So let's try this again. Another problem. And here we go. Let's suppose that the force of wind at each point x comma y comma z is given by f arrow of x comma y comma z equals angle bracket xz comma x minus y squared comma x times y times z. Okay. Now what is the work done? By the wind, described using this vector field, moving a leaf in a straight line from the point 135 to the point 4, 12, 20. Now, how it would be possible for a leaf to move in a completely straight line from one point to another is beyond me. I don't know how that would really happen in real life, but we're just going to go with it, just because it's going to make something nice, right? So just a note, um, though the question is written all physicsy, what we're really doing here is just we're finding the integral over the curve C of the provided vector field dot dr. That's all we're really doing. Where r arrow, just like we've seen already before quite a number of times, this just parameterizes the curve C. In this case, the line segment. The line segment. But yeah, we say parameterizes. Maybe I should put that in quotes, right? Because it's really a vector function. Okay, so to start our answer, the parameterization here would be r of t equals, well, how about just 1 plus, we're parameterizing a line segment, so 1 plus, and then the change in x from 1 to 4 is a 3. So 1 plus 3t. How about 3 plus, let's see, 3 all the way up to 12. I think the change is 9. So yeah, 9t. And then z coordinate starts at 5, ends at 20, so the change in z is 15. So how about 5 plus 15t? Okay. And then, oh yeah, t goes between 0 and 1. Now, from here, we need to build two things. One of these is f of r of t. So we need to feed in 1 plus 3t, 3 plus 9t, and 5 plus 15t. Plug those in for x, y, and z up in this right there. And when we do that, we'll get 1 plus 3t times, and then z is 5 plus 15t, comma, now we have x minus y squared. So we have 1 plus 3t minus, and then y squared. So 3 plus 9t quantity squared. And then we have x times y times z, the product. So we have basically multiply these components together, right? So we've got 1 plus 3t times 3 plus 9t plus, let's write that a little better, plus, yeah, 3 plus 9t times 5 plus 15t. Okay, so there's one vector, and then r prime of t. This vector is not so bad, so we look back up here, take the derivative one component at a time, we get 3, 9, 15. Now, the work done is the integral. So just that notation again, right? But what we end up with is, well, t goes from 0 to 1. So we have integral 0 to 1 of this vector dot that vector. Okay, so let's just write it out. Yeah, so I'll copy the 3 first. This time 3 times 1 plus 3t times 5 plus 15t. Okay, plus the next part of the dot product, 9 times this stuff. Let's get some parentheses in here. Yeah, 9 times quantity, 1 plus 3t minus 3 plus 9t quantity squared, close parentheses. I hope I'm doing this right. And then we have 15 times that stuff. We don't need to introduce any new parentheses there. So 15 times quantity 1 plus 3t times quantity 3 plus 9t plus quantity 5 plus 15t. And then let's just, for good measure, throw a set of parentheses there. That would technically be good practice, and then dt. This integral is probably a little tedious to do. It's not hard by any means, just would need to FOIL things out. Looks like we're going to have up to a t to the third. You're really just integrating a polynomial here, so let's not worry about actually finishing off the problem here. We'll just say, because we're talking about force, compute integrals of force? Well, Yoda does. Okay, let's set up one more here for this part. Hang in there. I know this is kind of challenging at first, right? So let's do the following. Let's integrate the vector field capital F, now being lazy and leaving out the of x, y, angle bracket 2 times x times y, comma 2x, over the unit circle, oriented in its usual direction, counterclockwise. Okay, so what do we say about the curve C that we're going to integrate over, the unit circle? Written as a vector function. I'll not use angle brackets this time just to change it up. Remember there's this ij notation as well. So cosine of t times vector I plus sine of t times vector j. And then you have 0 less than or equal to t less than or equal to 2 pi. We can go ahead and already compute the derivative of the vector function and have here negative sine of t times vector I plus cosine of t times vector j. F of r of t. Okay, so stare at this, but the x and the y that you see get replaced with cosine of t and sine of t, right? So you have 2 times, and then x gets replaced with cosine of t, and then the y here gets replaced with sine of t. And again, you could throw this in angle brackets, but I wanted just to practice the other notation instead because we don't write a lot of i's. Instead, let's just do this. Plus, and then over here it says 2x. So we've got 2 times, and then x is, well, cosine of t, right? So cosine of t, and then we need a j there. Okay, so that's f of r of t. And then the integral that we need to set up, the line integral over the curve C of the vector field dot d vector r is equal to the integral, t goes from 0 to 2 pi, of this dotted with that. Now, if we're doing a dot product, maybe it's a little easier visually in angle bracket form, but let's just do it. It should be this stuff times that, right? The coefficient of I times the coefficient of I. So we'll have, let's say 2 times cosine of t times sine of t. That's that stuff times negative sine of t. There's that part. Negative sine of t, okay, plus 2 cosine of t times cosine of t. All right, so 2 times cosine of t times the other cosine of t. And we'll write dt. And we'll stop that problem there. If you'd like to work out the work for this, it should be 2 pi.